Today we have the third lecture, and we'll talk about vector model of information retrieval. We have already discussed a part of vector model last talk, because the extended Boolean model used the weight construction from vector model, but today we'll focus entirely on vector model, so we'll not mix two models together. Okay, so I will talk about the basic model, the motivation, the term weighting we already discussed, the querying, and the inverted index implementation. Then also an extension of vector model to represent the texts by different, more semantic bases, which is called latent semantic indexing, and in the end of the talk also a bit about word2vec, which is not a representation and model for the whole text, but just a method for embedding words. But it's very useful for many tasks in information retrieval as well. So vector model, the motivation, here we have the first fully content-based search model, because the query is represented as a vector, and also the document is represented as a vector, and it's high-dimensional vector. High-dimensional meaning tens and thousands of dimensions, 10,000s of dimensions. We already had binary vectors in Boolean model. Now we will have real vectors. And the intuition or the reason for introducing vectors for documents is that we will measure relevance of a document to a query using distance of the query vectors in space. This is a homogeneous representation, unlike the Boolean model. In Boolean model, we had Boolean query, but vector representation, and was not very well integrated together and was problematic to provide user feedback and so on. In the vector model, this is much easier because everything is vector, and we can use vector arithmetics to play with things. It also follows the cognitive model, because the similarity search is a way how people recognize things. People compare things based on their similarity and then classify the things. And the vector model uses distance, and distance is the inverse concept of similarity. So it follows the cognition of a human. The vector model is the simple or the basic vector model is very simple formalism. It is highly parameterizable. It could be extended also to more sophisticated basis, and that's why we will also talk about the latent semantic indexing. This is one of the generalization to other base of dimensions than just terms. We will not have terms but concepts, and they are more semantic than terms. Also, because everything is vector, then also ranking of documents is natural, because we can measure the distance to the query, and the distance will induce us the ranking. And last but not least, because we have the vectors and we can do the vector arithmetics, we can also support relevance feedback by putting the vectors together and reformulating query and so on. Okay, so vector model, also known from other domains as the bag of words or bag of features model, is defined or named like that because bag is an informal statement for multiset. It's informal name for multiset. So multiset is a set that allows multiple occurrences of the same element. So we are also observing not just the presence of an element in a set, but also the frequency, the number of times the element is in the set. Therefore, we extend the model we don't have only words, but we have different numbers of words in documents. But the other properties are very similar to those in the Boolean model. We have vocabulary of M terms, so we have the same vocabulary of terms, and the vocabulary is processed by the stemming and lemmatization and these kind of pre-processing. And the document is also modeled by a vector of dimension M, but now it's not binary vector like in the Boolean model, but it's a real vector. So we have the documents as vectors in the space, and this is very high dimensional space because of the vocabulary is large. So for every term in the vocabulary, we have one dimension. So for some average English correct collection, we could reach up to 10,000 or more terms in the vocabulary. It could be more. For Czech, for example, it will be more because there are more forms of the word. Depends on how the lemmatization works, of course. So this is general picture how it might look like. So we have document 1 and its vector, document 2 and the vector. And this is only 3 dimensions because we suppose we have only 3 terms. One term is mountain, forest, nature. But in reality, we have thousands and tens of thousands words, but I can draw only 3 in the slide. Okay. The query, and this is the difference to Boolean model, is also a vector. Of course, it's specified by keywords, but these are not combined using Boolean operators, but they are just the keywords, nothing else. So the query is regarded as very simple document and is processed the same way. So no matter if the document has a big number of keywords or small, like in query, they are all processed the same way. So we get, again, a vector. And once we have a vector of query and vectors of the documents, we can measure the distance between these, and the distance is the opposite of similarity. And then we have the queries defined on top of that, and we can create rankings and do the search. Okay, so as I said, the space structure is simple. Each dimension is associated to a term from the vocabulary. So here we have only 3. And the value is the weight in particular dimension to the document. So for example, for mountain and document this document, DJ, there is weight 0.6 that says the term mountain is important to this document 0.6, like 60%, if we have bounded scale. On the other hand, the query has different weights, and therefore they are positioned differently in the space, and that's why we then compute their similarity based on the distance in the space. Okay. Of course, this is very simple representation of the queries and documents. It only relies on the statistics on the terms. It's the same way as in the Boolean model. In the Boolean model, we even didn't have frequencies. We only had presence. So now we have more information, but still it's very simple. It's only about the frequencies of terms. There is no order of the words. The semantic, the linguistic structure is lost. We have just the histograms of the terms. The term by document metrics we already had in Boolean model is the same, but instead of binary values, here we have real values. That's the weight. Basically, it's the same as in the extended Boolean model. In extended Boolean model, we also extended the ones and zeros to real numbers. So it's the same, and also it holds that the metric is very sparse because there are not many terms per document comparing to the dimensions. So let's say we have m dimensions, m terms, and therefore, for example, m is 10,000, but the number of terms is constant. Let's say it's 10, maybe 20, 100. So it's very sparse. And zero weight, for example, of course, is the same as in Boolean model. The term is not appearing in the collection. That's why it's so sparse. So it's 99% sparse. Now, how to construct the weights? Okay, this is a question we already answered very briefly last lecture, and but we didn't discuss the query weights because we had the Boolean expression. So we could maybe manually weight the terms that appear in the query, but this is not how it's done in practice, and everything will be done automatically. So we will automatically derive weights based on the statistics of terms. And of course, how to construct the weights, what is good and what's not. The intuition or the purpose of weights is to represent or to distinguish between important and non-important terms, but for a particular document. For one document, a term could be important, but for the other, it could not be important, based on the distribution, because in one document a term is repeated many times, so it must be important, because if it's repeating many times, that for particular document is probably the topic of the document, and that therefore the term is important. While in other documents where the term is not so frequent, it's probably a marginal topic. Of course, we cannot just say the frequency is one-to-one the importance, because then the stop words would be extremely important, because they would be very frequent. And so the problem of reducing very frequent but insignificant words, like stop words, must be solved either in the pre-processing, so getting rid of the stop words before we start to weight, or we can make the weighting system more complex and also involving this aspect of redundant words. And that's why we are using the TF-IDF scheme. So the TF-IDF, I already talked about them last time, but today more in detail. So the first component of TF-IDF is TF, and the TF is a normalized normalized variable for frequency. So what's the basic we have is the frequency of a term ti in some document dj, and this is the value we have. This is the feature of the bag of words. We have these frequencies. We get it from the parsing process. So we have Fij for every I and j. Then we will normalize this Fij, because if we do not normalization, then we get very incomparable interpretations of what's important and what's not, because some term could be very frequent in one document and less frequent in other document, but in the other document, it could be actually more important because the document has the total number of terms much lower. So that's why we must normalize the terms to have numbers between 0 and 1. And then the TFs will be comparable across different documents, no matter if the document is long or short. It's about the proportion of the terms now. So we will take the Fij and normalize it divided by the maximal frequency in that term vector, in the document vector, and that's how we get the normalization to 0 and 1. Okay, so this is DF. The second component is IDF, and the IDF comes from DF, and DF is the number of documents where a term ti is appearing in. So let's have a term ti, and df is the number of documents it is appearing in, and this characteristic goes against the tf, because when tf is high, then the term is more and more important for the document. If df the second is high, then is the opposite, because if the term appears in many and many and many documents, it becomes completely indiscriminative to distinguish between different documents, because it's everywhere. It's probably a noise, it's a stop word. So even if we don't remove stop words, then computing the weights using DF will serve the same purpose, because it will detect words that are highly frequent. And the component is computed as IDF, so we are not taking DF, but the inverse. And we take the inverse document frequency of term TI, which is the number of all documents divided by DF, which means we have a number between 1 and n, where the 1 is result where we have a stop word that appears everywhere. So if df is equal to n, we get 1 here. On the other way, if we have very rare words, just once appearing in a document in all the collection, then we get n, right? So n divided by 1. And so this is inverse, but in order to inhibit the effects of large numbers here, so the extremely rare terms, it's not taken linearly into the TF-IDF scheme, but this is taken logarithmically, because otherwise this would, without the logarithm, it would basically completely inhibit the TF, and only the IDF would be dominating and would basically create the weight for the rare words, for the rare terms. So finally, we have the scheme TF-IDF, which is TF times log n divided by DF. As I said, we have 2 scopes. We have the document scope, it's TF. No matter of the other documents, we have the proportion of terms in this document normalized, but we multiply this TF by the IDF, which is a collection scope measure that will basically align everything in order to not weigh highly words that are too frequent. So that's why IDF. This combination in experiments proved the best combination precision recall in general settings. So there are also other ways how the weights could be determined, but this is a kind of universal. It has also some cons. For example, the IDF component, because it must count the number of documents for a given term. It basically must recompute it for every new document in the collection. So it's basically assuming a static collection for computation, but this could be solved quite ad hoc by some solutions that update the index in batches. Okay, so these are weights. If we have an example, we have this example, we have a document that consists of 3 terms, and this first term is 3 times there, the second is 2 times, and the last one is just once there. So we have these 3 frequencies for 3 terms, and then we have also 10,000 documents and documents frequencies for the whole collection. So we have these 3 because we are now interested in these 3 terms. We have these 3 statistics for mountain, forest, and nature. How many of documents contain mountain, how many of documents contain forest, and how many documents contain nature. So this is these are numbers that could be used to compute the DF or IDF, and these are numbers that could be used to compute the TF. So with these numbers, we can compute TFs. So mountain is 3 times, and 3 is also the maximum. So 3 divided by 3, 2/3, 1/3, and IDF is n divided by df. So it's n is 10,000 divided by 50, 1,300 and 250. So we have these IDF, and this is the TF IDF values, and this is basically the vector of D. So this is the final vector we have computed. Just to note, this is the way for all of documents, so also for queries that are represented as documents. The difference is that when you have a query, we don't have here mostly not numbers other than just one, because we type a keyword query and we type every keyword once there, and okay, then that's query, keyword 1 is 1, keyword 2 1, keyword 3 1. Otherwise, it's the same representation as document. So we will also compute the query vector the same as the document vector using this pipeline. We end up with this vector, TF-IDF weights. Now we have constructed the weights and how to compute the similarity between the documents and the queries, and maybe documents between each other or queries between each other for different tasks. So we are talking about vectors, so we will use the angle between the two vectors. But if we consider the vectors as points in space, so not the vector, but this point, and this point, the natural choice is, of course, the Euclidean distance. So we could measure the distance between D1 as a point here and D3 as a point here, like this distance, right? And the distance between D1 and D2 as this distance, and D2 and D3 as this distance, the red ones, the red lines, right? But this is not what we would like to obtain, because if we think about how the weights are constructed, then the document 2 and document 3 are basically the same up to multiplicative constant. We have this vector is twice as long as this vector, but has completely the same proportion of the weights, of the dimensions. So these two documents, for example, are one is the same as the other, but this one is longer. Let's say we have concatenated 2 of D2 documents and we get the D3 because we have the same proportion, but there are more of the frequent words, there are more of the terms. Then in such case, measuring using Euclidean distance would not be appropriate, because this is very long distance in the absolute Euclidean distance. But much more different document is this one, because there is different pattern of the terms. There is a question. Yeah, that's good question. If we normalize, of course, we get the same. This is case where we have not normalized the vectors. In case we have normalized vectors, so they are all unitary vectors, then it doesn't matter if you use Euclidean distance or just the angle. But there is one technical problem with it. I will talk later about that. But okay, let's just continue with this unconstrained variant. So let's have vectors that are not normalized, they are arbitrary, and we measure distances. So in this case, this distance is shorter, Euclidean distance, than this, but the similarity of these two is smaller. So we would like to measure differently the distance than by Euclidean distance, and that's why we compute the angles and not the absolute distances. Okay, so for the angle computation, we have two ways how to compute basically angle, or a measure that is equivalent in sense of searching with angle, and that's the inner product. Is the scalar product, right? So it's just multiplication of all the pairs of the components in the two vectors and their sum. And we have the cosine similarity, which is again the dot product, but it's normalized by the distance of the both of the vectors. Basically, if we have normalized vectors, so you asked already if they are normalized. So if we have normalized vectors to unitary vectors, then these two are the same because they are already normalized, and we would divide by 1 here. And so what we get is the cosine of this angle. That's why the name. And cosine of this angle, we can get the angle from that using function arcus cosinus. But this is not necessary because we are here in one of the quadrants. We have positive weights, and therefore there will not be higher angle than 90 degrees, right? So we have p half, the maximum, pi half, the maximum angle, and from 0 to pi half. And on this interval, the cosine function is monotonous, and it's decreasing from 1 to 0, right? And therefore we are okay with the cosine because it's strictly inverse to the angle on this interval. So we do not need to compute the arcus cosine. Okay. The inner product or cosine similarity is a real similarity. Similarity in the way that the higher the number, the more similarity. It's not a distance. If we would like to make it a distance, we must either do the arcus cosine, then we get the angle, and that's the angular distance, or just simply take a 1 minus this, and we get cosine distance, for example. It's the same in terms of the ranking that we will get when measuring the distance between Q and DJ. Okay, and now we need to formulate or create the queries on top of the similarity function, the cosine measure, and we can formulate a so-called range query where we have the vector of the query vector that was created from a document or from keywords that we provided. And then we must provide also a similarity threshold that defines the extent of the query. So this is the query vector. And this angle basically is the threshold that defines how far from the query vector we are interested in the document. So every document that falls into this segment, the blue one, is the answer to the query. So these documents must be returned as an answer. Of course, in practice, we are more, we have not this threshold, but we have only so-called KNN query. We have the K nearest neighbor query, where the K is the number of the nearest neighbors, nearest documents that should be obtained. And that's the second type of query that cannot be nicely drawn like this because we don't know the threshold. We only know we want to 10 documents, but basically they are evaluated more or less the same. For the KNN query, there must be employed some heuristic that basically approximates the threshold, but otherwise it's the same. The result of a query, either range or KNN query, is a set of documents that is ranked because we have now the distances, the similarities, so we can rank the result from the most similar to the query to the least one. So this is natural property of a vector model that providing a ranking to a query. And what is also nice about vector model is that we can very effectively support the relevance feedback. Relevance feedback is the interaction of user that based on the results in the first answer, the user can basically annotate some of the results as good and some as bad, positive and negative examples. And based on this choice, the algorithm of the user feedback can reformulate the query. Basically, not reformulate the query itself, but shift the query vector. And this is very easy because if we have this original query queue and we got 4 results, these 2 vectors and these 2 vectors, and the user marked these 2 vectors as positive examples, meaning that these documents I wanted to return, and these 2 as negative examples, meaning these 2 I didn't want to return, these are bad. Then the algorithm in the next iteration can basically prefer the documents that have vectors close to these ones. And this could be done very easily by basically adding to the query vector these 2 documents and possibly subtracting these 2 documents. So we are shifting, using the vector arithmetics, the query vector from here to here. And in the second iteration, the user will get again the positive he already marked, but these are too far now, so maybe they are not returned at all. But maybe there is some even completely new one return, and maybe it's positive, and so the user gets more satisfied. So there is improved the effectiveness of the search using the loop of relevance feedback. Okay. Now the implementation, that is very similar to the Boolean model. We have again the inverted index. And in inverted index, we represent the term vectors, right? So we have the term and the vector of documents the term appears in. So this is the compact representation of only IDs of documents where the term appears in. So there are not covered documents where it is not. So basically, those cells in the matrix where there are zeros. So we have only non-zeros here. And in addition to the Boolean model, we don't not only have the IDs. This is ID 3 document 710, which is in ascending order, but we have also extra information about the weight of the term in that document. So this is 0.3, 0.2, and so on. So this is extra information. Otherwise, it's completely the same inverted index as in Boolean model. And if we want to use this inverted index for querying, it's again very similar to the Boolean query, because we again need the merge sort style of aligning cursors in different lists corresponding to the terms we are querying for, because what we have in the query, these lists must be processed. But instead of evaluating a predicate, Boolean predicate on this document vector that is across multiple terms here, we compute the cosine similarity between the vector and the query vector, because the query vector is already known. So here is an example. We have the inverted index here. The gray are terms that are not used in query. So in query, we have forest mountain nature. Using TF-IDF, there is a computed query vector for that on 5 terms, but only 3 are non-zero. And we have also the threshold for the range query, which is 0.5. And now we need to process the query. So what do we do first? We align to the least ID of the document that we encounter in any of these terms. So we have these forest, mountain, nature, and we align on the first document, which is document number 2, where we have nothing. So there is no 2, so there is 0 because it's not stored, so it must be 0. There is 3 already, so 2 is here, but it's zeros. And here it's 0, 0.2, 0.9 right here. And if we take the query vector and compute the cosine similarity with this reconstructed document 2 vector, we get 0.74. And this exceeds the threshold 0.5. So what's exceeding 0.5 goes to the result, because remember, cosine similarity is similarity. The higher, the better. The higher, the more similar. So it must be more similar than 0.5. It's 0.74, it's higher. So it goes to the result. Next, align to the next document. So the next is 3. So we have here 0.3, and it's not here, so it's 0. And we have 0.3, 0.6, and 0. Cosine measure with this is 0.12, and this is too small. So it goes not to the query because it is not above the threshold. And we go further. So document 7, 0.2, 0.6, 0.3. Okay. No, 0.6, there is nothing. So 0 and 0.3. We have this. We have the 0.28, and it's too small. It goes not in the result, and so on. 8, it goes. 9, it doesn't go. 10 doesn't. 15, 16, it goes. 17 goes. 18, 20. So you can see that from this number of documents, 4 of them go to the result. And these are here, and they are even sorted. It's ranking based on the similarity score. So the most similar one is the document 17, 0.77, because what we have 0, 0.5, 0.8, we have here 0, 0.1, 0.8, so, and it's 9, so it's basically based on the last one that is most similar. That's why it ranked so high, but it's still not 1. The 1 would be complete duplicate. Okay, so everything's clear from this example. Okay. So again, I repeat the advantages of inverted index. We have already compact storage of the metrics, so not storing the zeros. And we have also very effective processing of a query, because we only process the lists for terms that appear in the query. 99% of them remain untouched. So we really process very small portion of the whole structure. We have also the Boolean queries for free using this inverted file, because we have basically the same information. We have more information for the vector model, but we can induce also the bits, the Boolean information, because everything that is stored here is basically appearing in the document. So it's true, the presence of the term is true. So we can also use this for Boolean queries. Okay, this is what I already discussed. And now, second reason why to use the inner product and not the Euclidean distance. The first was already discussed. If we have the absolute distances, Euclidean distances, it could really be invalidating the relevancy for differently of the documents of different lengths. But even if we have normalized vectors, then still we use the inner product, because this is in inner product we have multiplications of the weights, right? And this is basically the necessary condition to use the inverted file, because in inverted file we can skip all of these gray lists, because here their weights in the query are 0, and because 0 times anything is 0, we don't care what's here, because we would otherwise multiply by 0, so it's useless. But if we use the Euclidean distance, there is not multiplication like here, but there is subtraction. So we would be subtracting from the 0 something that is not 0, and the result would be not 0. So in this case, we cannot use the inverted file like that. We needed to really process all of the lists when using Euclidean distance, and this is complete fail in terms of effective search. So that's why we are using inner product, because this multiplication supposes that we only multiply non-zero elements. Otherwise, it's always zero if this one or this one is zero. Okay, so this was one big reason technical reason for using the inverted file and cosine measure. The basic vector model, there are pros and cons. So it's much better and more homogeneous model for retrieval of information, and it's geometric. It's not combination of Boolean and vector, it's just vector model. Therefore, we define query is the same as the documents, and therefore we can query by example, because we are in space with one representation. We can choose one of the documents, for example, as a query, as example query, or as an example, it defines a query, or we can create our own query using keywords. No matter how we create the vector, they are the same as document vectors. We have also ensured the ranking because we are measuring the similarity, the cosine measure, and this serves us for sorting the documents from the most similar to the least one, from the most relevant to the least one, and therefore we get naturally a ranking. And therefore, if we have ranking, we can also easily control the size of the query, the query result. So we can just answer the query for 10 nearest neighbors, 10 most similar, or we can in this ranking we can choose the length of the prefix in this ranking anyhow. It is also efficient because of the inverted index, and it's kind of effective, but this could be also improved because as such the model is too simple, because we have more homogeneous geometrical view on that, but we don't have the possibility of combining terms we had in the Boolean model. In Boolean model, it was more complicated, but it allowed us to really do strong conditions, like this term yes, and this term must be together there, and this must not be there, or these two be together, but not these two be together, and so on. In vector model, we don't have this. We only say these terms, compute the vector, and measure the cosine similarity. And this is not a very large expressive power of the model, and it also lacks the higher semantic processing, because the terms, and this is also the problem of the extended Boolean model, but here it's more pronounced in the vector model. The terms are used as dimensions, and the dimensions are supposed to be orthogonal to each other, right? Because it's coordinate system, right? We have orthogonal dimensions. So in other words, we assume independence of terms. So we assume that all terms are different from each other, and they are different the same. They are completely independent. But this is in normal languages like English or Czech, this is not true. If we take pairs of words, they have some correlations between them. Some are basically synonyms, for example, or homonyms, or they have different relations. So we cannot definitely say that this assumption of term independence is correct. And that's why the vector model alone on this primitive level cannot be as effective as if we really include this correlation of terms into account. And that's a motivation for introducing the some extension of vector model, or some transformation of the vector model to another model. It's again vector model, but now we will not represent dimensions for terms, but for something else that already is orthogonal to the rest of the dimensions. there is example how to motivation example why to do that. We have to, for example, we have two documents. One is about, it's like title, right? So it's about more people look for jobs, and the second is unemployment is on rise, right? So if you just interpret these titles, the both documents basically have very similar semantics. So it's about people having no jobs because people look for jobs and there is unemployment, right? So people have no jobs if there is unemployment. But if you take it strictly on the basis of terms, there are no terms in common here, right? So there's people, jobs, unemployment. So if we have vectors for these two documents, they will be completely not similar because they even do not share terms. So these would rank as completely dissimilar, although they should be ranked as similar because they have similar semantics, but not on the level of terms lexically. On the other hand, we have different examples. We have other two titles. George Bush fires his secretary and fires an Australian Bush got strength. And there are two terms in common in both of the documents. It's Bush and fire, right? So these two documents look, based on the terms, they are very similar because they share two terms, but they are not similar because this is about president that fired secretary and this is about real fires, right? So it's completely not relevant. But using the vector model, we get the opposite we would like to have in both of these examples. And this is the consequence of not having something more semantic than terms, because terms are too low-level representations. So instead of terms, we would like to have some higher-level concepts that basically represent more robustly what is behind the terms, like that. So they will group similar terms by semantics, not just by the matching of the lexical forms, right? And as such, it also solves the synonymy and homonymy, like here, and it has many other effects. And because there will be much small number of concepts that will be high level, more general, it would be also the reason why we get method for dimensionality reduction. We get much smaller number of concepts than terms because we are going from low level mass of terms to higher level, not mass, but higher level set of concepts that is high level. Therefore, it's much less number of concepts. But what is concept? We can, of course, create concept categories by mapping terms into concepts manually, for example, or using some ontology. We can maybe download some Wikidata ontology or something and do this mapping. But this is two things together. We could stay with the data we have. So we have the collection of the texts, and we need to solve the query. So just to query. We don't have any third-party stuff like ontology or something. We have just this. And even using this basic collection, we can somehow create concepts. And the way how to do is to use so-called method of latent semantic indexing that is itself using SVD, which is singular value decomposition of the matrix A, which is the term by document matrix we already have, into other matrices. So this is the decomposition. We have three matrices that together form the matrix A. And using this decomposition, we are able to transform the data from the basis of terms into the basis of concepts. And now what are the concepts? The concepts basically are frequently appearing linear combination of terms. That's what it is. They so the concepts are not some nicely human labeled concepts. They are only frequent linear combination of terms appearing in the collection A, and these concepts are then stored in this matrix sigma V. In the matrix U, we have the basis for the concept. So here is the mapping between the terms and the concepts. So it's also mapping. This matrix could also be used to transform from the basis of terms into the basis of the concepts. Basically, that's how these values were created during the decomposition. And what's semantic about that? Basically, the semantic is borrowed from the collection, and it only basically statistically computes or translates from the documents the patterns of terms that are appearing together often into the concept. So if they are still repeating the same terms together, like for example, we could have a document about operating systems, and there will be a word Linux, kernel, bash, I don't know what. So then, or maybe another document, and then will be other words with Windows, I don't know, processes, threads, whatever. Then these frequently appearing patterns will materialize as concepts, then get high so-called singular number. Here it's like eigenvectors and eigenvalues. So here we have singular vectors, singular values. It works very similarly, and they are sorted. So we have concepts with the highest frequency ranked as on top, and they are decreasing with the singular number. So we get the most strong concepts appearing in the collection, and therefore we can do the decomposition not as full decomposition here, but as a rank K decomposition by only considering these gray parts of the whole decomposition. So this is the whole decomposition, and we only compute these parts using numeric methods. And there are two effects for this, or two reasons. First, it's faster because the whole decomposition is really, really expensive. Time is expensive. The algorithm has high complexity. And second, because we have sorted the singular values here and the single vectors here, we can only take the most significant one and omit the rest. Everything what is white is not significant. And so it also contributes to more robust representation of the vectors, because the noisy vectors, the noisy concepts, so these concepts are combinations of terms that appear not so often, and therefore they basically act as noise. They are excluded, and we get only the very strongly exhibiting concepts that are here. So we get for free the dimensional reduction using this, because we compute only k of the singular vectors, k singular values, and k vectors of the opposite transformation. And once we get this multiplication, we get still the number of documents, because this is n, right? This is n. Okay, what we get is some distribution of singular values in the matrix sigma, and we can observe that the singular values is like eigenvalues. They really quickly drop from this is normalized, right? This is not 1, but this is normalization, so 1 is higher. And it drops quickly. So first, I don't know, 5 concepts are very dominant to the whole collection, and then all other concepts are not so dominant, right? So after some 50 or something, we have enough dimensions for concepts to express all of the documents, and we get dimensional reduction from the tens or hundred thousands of terms into just hundreds or thousands of concepts. And this is huge, 2 orders of magnitude reduction of dimensionality. But everything comes with cost. And yeah, I will show the cost later. But first, what I need to express is that basically we have 2 components coming from the decomposition. First is this sigma times v, and that's new representation of the matrix. We decompose the term by document matrix is now turned into so-called concept by document matrix. So the data are now expressed in the basis of concepts, not terms. So there is much lower number of concept columns in the matrix than it was. And the second is the matrix U, which is basically the basis matrix, and it's also the projection matrix that we use if we want to project some vector, for example, the old query into new query. So this query is in the term space. When applied to U, we get the same query, but in the concept space here. And in the new space of concepts, we still use the cosine similarity because we are still in some vector space and we still have the coefficients of and weights. We still have the weights. So we still use cosine similarity. What is not the same is that we got very dense metrics. So we started with a very sparse matrix that had very large dimensionality, but was nicely indexed using the inverted file and was compacted because it was not storing the zeros. Now we have very dense metrics. So from one hand, we have very small number of concepts, so reducing the number of rows here, but for the price of having everything very dense. So we have this dense matrix, and also the query vector is dense because everything that basically is projected using this matrix is then dense. No matter if it was a document or a query or everything, so it's dense. So now it's useless to use inverted file on this matrix because this matrix is already very dense and the query is very dense, so it does not make sense to use inverted index because inverted index is only efficient if we have very many zeros in the query and only few non-zeros. But here we have only non-zeros here, so we will not store, we will not save any computations. So it's better to take really the whole matrix and do the brute force computation of the cosine similarity here. So this is LSI. Of course, this is what I mentioned right now, but we could maybe use the brute force sequential processing of the query or use other indexes that respect the natural distribution of the data in the space, but are not based on the inverted index. There could be, for example, metric access methods. We will also talk about them. So to conclude, we have pros. So the LSI model reveals the latent semantic. So it's basically another step on top of the classic vector model that transforms the incorrectly assumed non-correlated terms into correctly uncorrelated concepts, because these concepts are really orthogonal to each other. The vectors of the concepts are really orthogonal to each other, and therefore the correlations from the terms basically transformed into the concept themselves, but then no correlation left. That's why now are truly independent and orthogonal. So we got this. So this is good to have uncorrelated dimensions. We got dimensionality reduction, and of course we got the robust behavior and the more semantic based search, because we have concepts, not just terms, so we can solve problems of homonymy, synonymy, and so on. So that's why LSI is good for. But there are also some cons. First, the concepts are not some magically created concepts that are human readable, because this is just, they are just linear combinations of terms. Also, it's just matrix algebra, so this is not machine learning, right? So in machine learning we can train, because in machine learning we provide annotations to what the machine should learn, but here it's unsupervised, there are no annotations, and therefore we get just statistically significant linear combination of terms. That's it. We cannot name that. For example, here we had names of the terms, database, vector, everybody understood, but here now we have concept 1, concept 2, concept 3, and we cannot name it. We can just really describe it by the linear correlation, and the linear correlation, of course, can also include negative weights. So it's quite tricky to interpret. Another cons is we have the dense matrix and dense query vector, so the inverted index is out. And of course, we have also very expensive algorithm for the SVD, for the singular value decomposition, that is quadratic and cubic in NMN. So this is not scalable method to do on web scale collections, but it's quite usable on medium or small sized problems. Like you can have smaller collections, smaller corpuses, you can do their LSI and maybe use this external information, use this as external information for creating basically some ontology on general text. And this could be later used for the large scale searching. But in this form, the LSI is only used for processing of the corpus that basically serves as vocabulary or ontology for the large scale cells search. We cannot use it on the huge matrices. Okay, so that was LSI, and the last what we have here is the word2vec, and word2vec is also about vectors, but it's not representation for the whole documents, but it's a representation for single words. So we take one word, and create vector of that word, or it's also called embedding. We create embedding. Now this is already a machine learning approach, and it's unsupervised again, but it's machine learning. It's not just simple matrix algebra, but it's more heuristic, because yeah, we are using their 3-layer backpropagation neural network. It was invented by Tomáš Mikolov. At that time he was in Brno, and basically the word2vec works for words, but we can embed also other types of data that is symbolic. So we can use this technique and extend it to any symbolic data. So symbolic data, so word is symbolic, right? We have a string of characters, so they are symbols. We can have string of other characters like genes. We have sequences of genes. We could have sequences of likes and follows on Facebook. We could have sequences of playlists of songs, and so on. So if we have any sequence of symbols, no matter if it's word or something else, we can use this to embed it to a vector, and then with this vector representation, basically reuse the benefits of the vector arithmetics we already experienced in the vector model to search in data. And this is because it's embedding based on machine learning. It also works on some corpus that is using as a training data. And then the final embedding has the property that semantically similar entities are close in the space. So we have vector space, and similar things in the space are close, and non-similar are far from each other. So that's how it's intended. And now how it's done. There are two variants, or word2vec of the original word2vec. but both of them basically represent or embed a word. So let's suppose you have a corpus of data. And in our example, it's just this one sentence. And we have this sentence, and we want to embed this word cat into a vector. And because we don't have any annotations to that, we must take the context of the word cat in that corpus on the text as its own annotation. So we basically take the neighborhood of the word as its annotation. So it's some analogy to saying, okay, who I am, I don't know, but maybe my relatives can say what I am, or my neighbors, right? So this is the same. So the cat, the embedding for cat is not determined by the cat itself, but by the neighborhood of the cat. And how it's done technically? Technically, we represent every word, every term, using so-called one of V coding, or one hot encoding, where we already have the vocabulary. So this is similar of what we had in the vector model. So we have vocabulary that has size V now, right? So this is different terminology. This V is the same as was M in the vector model. So here it is V. So any word here could be encoded with one in place that corresponds to the dimensions of the term. So for example, if cat is in the vocabulary here, so there is one, and everywhere else is zeros. That's why it's called one in V coding. So every word is encoded like that. Right? So we have vector coding, is initial coding of words here. In projection layer, so this was the first layer. So in first layer, this is the input layer, and it accepts all of these codes in this vector using these neurons. We have 3-layer neural network. So this V values goes here. Right. Or maybe no. We have this is already the context. This vector goes to one of these. So right. So this is one input for one word. This is second input for the second word, and so on. So we have in this input we can basically feed into the model the whole context. So all of these words, 1, 2, 3, 4 words goes 1, 2, 3, 4, right? And every of these words is this vector. Then at the end, on the projection layer, we have the representation of the focus of the center word, which is the cat and the encoding for a cat. So now what we have a pair of set of vectors for the context and vector for the center word. And we can do this. We can provide this model with many of these pairs and train by backpropagation this model that is called continuous back of words. We can also do this, the opposite. We can, this is how we predict from the context the actual center word. We can do the opposite, and we can predict the context from the focus word. So this is completely the opposite. So we are putting on input cat and predicting the context, and again, backpropagation. Both of the representations have different properties, right? But what we get, we learn this model, and then on input, and then we have representations, not the nominal ones, but the learned, basically these weights here on these connections for every word that we got here. So we have the embedding of cat here, finally, right? And once we have the embeddings of the words, we can then project, visualize them in space and work with their vectors in space and look how they are similar to each other. So for example, it's nice to see that we could maybe do also machine translation using word2vec, because if we take English corpus of text and we take Spanish corpus of text and do embeddings using word2vec, using one corpus and the other corpus, we get very similar distribution of words that basically correspond one to each other. So this is the distribution of numbers, 1, 2, 3, 4, 5 in English. And this is the distribution, and this was trained using the English corpus, and this is the same for the Spanish corpus and Spanish numbers, right? 1, 2, 3, 4, 5. And you see the very similar distribution of the terms. So this is in different space, right? The same with other words like animals, cat, horse, cow, pig, dog. And this is in Spanish the same, gato, caballo, faja, and so on. And it's also very similar. So using this, the machine translation could be very, very effective. We can also do vector arithmetics like this. We can take embedding for king, for the word king, subtract from the vector of king a vector of man, then add a vector of woman, and basically we get a vector of queen. So if we do these operations and then do separately embedding of queen, we basically get the same. So this could be validated. And this is very nice because this couldn't be done on the lexical basis. You cannot just subtract man from king if you have the 4 letters K-I-N-G and M-A-N. How can you subtract semantically to words? You cannot do that. But once you have embeddings and you have vector representations, you can do this kind of magic, right? So we get a queen. Or we can, for example, induce new forms of words. So for example, if we had walking, and we know that walking has a past tense walked, and walk is embedded in like that, and the vector goes in this direction, then when having swimming and swam, 2 words, and we already know that this is just rule that for some verbs, putting ed to the end gets the past tense. Then if we don't know the irregular verbs, but we know that there is a swimming and we have the same direction vector here, then swam is probably a past tense for swimming. So these are these vector arithmetics could really help in natural language processing and retrieval tasks of many kinds. Here we have, for example, how relates China to Beijing, Russia to Moscow. Again, you can see that there are very similar relations between capitals and the countries, right? So there is very similar. And again, this is not a magic. This comes from the corpus that is used as training data. And because this is in similar distribution, the Beijing is appearing in similar contexts with China than the others are. Then that's why they have very similar links or embeddings in space. Okay, so that was word2vec or basics of word2vec. It could be generalized, as I said, to any symbolic sequence. It is different from vector model of information retrieval because it's representation for words, not for document. Document is different. We have the back of words here. But it could be compared to LSI, because in LSI we want to uncover the hidden semantics, and we did it using the decomposition using SVD, and we get directly representations of documents in LSI. In word2vec, we basically do the same, but on the scope of individual words. But it could work very similarly. So we can take the word2vec representations of words and use it in vector model. So we can combine these two together. So basically, there are some similarities between these two. Because word2vec is machine learning approach, it could be It could be implemented heuristically on the models of neural networks and so on. So it's imprecise, it's approximate technique. So we don't need to really compute the huge decomposition. So it probably also leads to much faster and scalable search. And it also performs better because it's not mechanically decomposing the metrics, but it basically uses just the context, and so there is retained the linguistic features of the text, because in word2vec we really have these windows, and there is only small window over the whole text, so these keywords are really close together. And this is different from LSI, because it's different from the vector model, because in vector model we only have the frequencies of the terms in the documents, no matter where they were located. So in vector model we completely lost the order of the terms, but not in word2vec. So these are some features that make the word2vec working very good. Okay, so that will be all for today, and there is time for questions. So do you have questions? Okay, there are no questions, so we will see next week. Goodbye.